So let's take a look at another spectroscopy problem with NMR, infrared and mass spectroscopy. This latest one, if we look at the data, we have got some interesting peaks in the infrared. We've got the molecular ion peak at 106 from the mass spectroscopy, and also some nice patterns with some downfield shifts for the nuclear magnetic resonance. Feel free to take a second and pause the video and try and work out the structure. Okay, ready for the answer? So let's look at the infrared first of all. And our first big peak here is at 3028. Now that's above 3000. So although we're looking at a carbon to hydrogen stretch, it's not a normal alkyl stretch. Stretches for the carbon to hydrogen bond above 3000 are normally only for an aromatic hydrogen, an alkene hydrogen, or an alkyne hydrogen. As we look at the spectra, we don't see a strong peak in about 2200 for an alkyne, so it can't be that. We don't see a strong peak or a moderate to strong peak between 1680 to 1640 to suggest an alkene, but we do see these peaks at 1600 and 1500, which suggests that we have an aromatic molecule. So sure enough, that 3028 peak is for the carbon to hydrogen stretch for a hydrogen which is attached to the benzene ring. And then our 1606 and the 1498 are the carbon to carbon bond stretches for the aromatic ring as well. One last clue, which is in the infrared, is look at those jagged little peaks between 2000 and 1600. And that's a classic kind of fingerprint pattern for an aromatic, what we sometimes term as overtones. So it looks pretty definite that we have an aromatic molecule here. Let's see what the mass spectroscopy data can tell us. So as we said earlier, our molecular ion peak at 106 doesn't look like there's any other functionalities from the infrared or any other halogens, isotopes present from the mass spectroscopy. So if we take that mass of 106 and divide by 14, the mass for each CH2 unit, it goes into the 106 neatly 7 times, giving us a remainder of 8 units of mass. So we could imagine that instead of the 7 carbons, there's actually an 8th carbon if we use those 8 units of mass and steal another 4 hydrogens from the chemical formula. That would put the carbon up to 8 and the hydrogen down to 10, and that should be a final chemical formula for this molecule. Of course, for a molecule with 8 carbons, if it was fully saturated, that would suggest 18 hydrogens using our CnH2n plus 2 rule. For every 2 hydrogens that are missing from that count, it suggests a degree of unsaturation. So 8 hydrogens down at 10 instead of 18, it suggests we've got 4 degrees of unsaturation, which is probably going to be 3 pi bonds and the closing of the ring. So the mass spectroscopy definitely suggests again that we've got benzene. If we look at the nuclear magnetic resonance data and take a look at those peaks, right away we can see those peaks at the 7.4 to 7.3 range, downfield and right in the middle of our range for hydrogens on an aromatic ring. That's very distinctive, and the splitting pattern is a little bit muddled, but the integration is for 5 hydrogens. So basically we've got an aromatic ring with 5 hydrogens and therefore just one position which is still to be substituted. Because that comes in with our peak at 2.75 ppm and 1.35 ppm. If we take the 2.75 first, it's split into a quartet. So the two hydrogens have got three non-equivalent neighbours, n+1 rule. And then the peak, which is at 1.35, for three hydrogens split into a triplet, is the complementary peak to the peak at 2.75. So two hydrogens here, hence the splitting into a triplet, and three hydrogens here, hence the splitting into a quartet. So a methyl group to finish off the molecule, and it gives us a final structural formula.